Hello, and welcome to the webcast titled Control Data Chaos at the Edge with Next-Gen Processing Solutions. My name is Dan Taylor, Technology Editor with Military Embedded Systems, the SOSA Special Edition, and the FACE Special Edition. I'm also moderator for today's event. To learn more about Military Embedded Systems, please visit militaryembedded.com and check out our articles, blogs, and podcasts on military technology. Our speakers today are Justin Myers, Principal Product Manager for Mercury Systems, and Tim Woodard, Senior Solutions Architect for NVIDIA. The event is sponsored by Mercury Systems and hosted by Military Embedded Systems Online and Open Systems Media. Before we begin, I have some housekeeping items. This and all Open Systems Media webcasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This webcast will consume about 30 minutes, leaving the remaining time for the question and answer session. Some of you might notice that our console has a new look and feel for 2023, so let me show you around. You'll find on the right-hand side an area where you can enter your questions in real time. We encourage you to ask questions throughout the session while the question is still fresh in your mind. We'll address as many questions as we can during the closing Q&A portion. If you have a question for a specific speaker, please note so at the beginning of your question, or I will offer the question to both our speakers. If you have a question pertaining to the event operation itself, one of our technicians will get back to you during the webcast. Please note that as much as we'd like to, we may not get to all of your questions today. In that case, someone may get back to you after the webcast with more information. Across the way on the left-hand side, there's a resources section, and that's where you can find the slides being presented today. Below that, you can view today's speaker information. Two additional features that we're really excited about. Number one, your console is now customizable insofar as you're able to manipulate all of these widgets, Q&A, resources, and presenters for your ideal viewing experience. Expand them to get a closer look or close them to have the presentation window automatically resize around them. For maximum screen size, close them all and or utilize the full screen control in the upper right-hand corner of the presentation window. To bring them back, simply click on the buttons in the bottom middle dock. Number two, in an effort to make our webcast more accessible this year, we have added closed captioning capabilities in nearly a dozen languages. To enable this functionality, simply click on CC in the upper right-hand corner of the presentation window and select the language of choice from the drop-down menu. This webcast will be archived online at the same URL you used to join today's live session and will be available within 48 hours. Once up, it will be available for at least 1 year. One more quick note before we get started. Shortly, we will open a poll for everyone here. We would appreciate every attendee's feedback. Now, I will get us started with market drivers and trends. One of the biggest driving factors in the market today is the Defense Department's insatiable demand for data, particularly from systems at the edge, such as ISR, electronic warfare, and radar. This is fueling sensor processing solution development. It's a market that's getting bigger. A recent report from Verified Market Research predicts that the global C4ISR market will reach $178 billion by 2030 for a compound annual growth rate of 4.84%. NVIDIA is a major player when it comes to secure signal processing solutions that enable AI at the edge, and Mercury plays a big part in initiatives like the Sensor Open Systems Architecture, which enables faster tech deployment. NVIDIA is a market leader when it comes to processing at the edge, particularly for defense applications that rely on super-performing processor solutions that can enable AI. The Defense Department is a major consumer of commercial microelectronics like semiconductors, FPGAs, and processors. Companies like Mercury help bridge the gap between the commercial and defense sectors in this area, making commercial processing tech available for defense applications like EW, radar, C4ISR, and more. Both Mercury and NVIDIA ensure a trusted supply chain for the Defense Department. With that, let's talk about the process with our guests. First up is Justin Myers. Justin?
Yep. Thank you, Dan, for the introduction. So today, as we've discussed a little bit, we're going to be specifically looking at how do we actually handle the mass quantities of data that we're collecting in the world around us. And we're going to do that by first taking a look at what actually goes into classification algorithms and how they're built. And then we're going to look at the software tools and the actual hardware that's being developed today and in the future to actually use the vast quantities of this data and to draw upon it the inferences and the predictions that we actually need to be successful. We're then going to do a little bit of a quick look in the future improvements that are required, and then finally the implementations of where they're coming in today. So without further ado, let's demystify a little bit what actually a neural network is and how it's actually used within our industry. The first example that I can give is actually it draws upon the natural processes that we have inside of all of us when we create inferences on the world around us. For example, sitting in your office or sitting at home, you can hear sounds outside of the building. And without collaborating with all the other senses that you have available to you, you can make predictions and inferences to actually understand what is happening outside and what you are perceiving around you. For instance, you could hear the sound of an automobile and already classify it in your head that that's where the sound is originating. And the moment that you add additional sensors, i.e. your eyes or your smell, you can actually classify it then at varying levels of obscurity all the way down to make, model, and even manufacturing year, if you have already trained those neurons to fire in that way. And we do this with computers through developing these matrices of neural networks. And they can be as complex as we need to actually dive into that layer of complexity for the information we're trying to pull out of it. But at the core level, what we're doing is we're taking those input values and we're actually weighting them and applying a bias associated with each of the neurons to actually reach the output that we're looking for. So we look at the neural network, and there's mainly three layers that actually the data is parsed through. The first of which is that input layer, which is what I was describing earlier in the terms of a natural occurrence where it comes to the sound being heard outside of the building. But for computers, they can be as complex or as simple as we need them to be. They could be a single node neuron where there's only one data point that we're building an inference upon, or there could be a million, that is as many sensors as we can feed into the system. And then from this input layer, the data is actually passed and used to build values and to create this synthetic neuron firing environment inside of this hidden layer, where each of these neurons have a little bit of a part to play in building these inferences and actually processing that data through the chain so that we can finally create the inference, that output layer. And once again, this output layer can be as complex or simplistic as we need it to be to build our models. They can be as easy as a binary function where we're seeing either a 0 or a 1, or they could be a probabilistic equation where we're trying to find the most likely outcome with the data that we have ingested. And these neural networks, once again, we can build them to define as deep of the information that we need it to be, whereas the output layer from one neural network could be the input layer feeding into a following assembly that's going to be a deeper dive into the data that we've received and that we're using. So let's talk about actually how we actually use that neural network and flow through it. There's two main sections when it comes to training and utilizing neural networks. The first of which is that forward pass, where we're taking those data points and arbitrarily moving through the system and then finding output layers and taking those predictions and using them. And then there's the other part, which is the true training, which is that back propagation, which is feeding back and building the model and making it more and more accurate when it comes to these predictions. So as I said earlier, that forward pass is actually the feed through the system that reaches that output layer and that we can build upon these predictions. And we do this by looking at the previous layer and then pulling in all of the outputs that we received at the neuron level and then passing it to the next neuron and rolling it all the way through. And we do this, as I said at the beginning, by taking the previous layer, applying a weight to it, and then taking a neural specific bias. And that is the value of that neuron that we work through. Of course, you can apply activation functions that we can apply to it to either make it fire or work in a specific way, but that's a little deeper in the weeds than I intend to go to today. And then the back propagation. This is actually the magic of how a neural network actually works. And we use this specifically when it comes to a controlled data set to actually build upon the neural network and actually make it classify these natural occurrences or these sensor data points to create predictions that we can use for data outside of that control set. And it works specifically by taking the gradient or the specific value that a variable holds in this matrix and applying either a left or right movement and a magnitude associated with moving the control data points closer to the predictions that we're hoping to accomplish. Of course, we do this carefully so that we don't overfit or underfit the functions. But as you can see on the right a little bit, is just an example of the chain rule, which is the representation of a gradient, where we're actually developing the algorithm to take the specific elements of each of the equations that went into building that forward pass and weighting those variables associated with the specific changes that we're looking for. Of course, the gradient itself can be even more complex than what we're working with when it comes to developing these algorithms. And that leads me to basically the core value, which to make these neural networks actually work, you need to parse through that data and do the forward and back propagation as many times as needed, upwards to millions of times, to create these data sets that are truly robust enough to work at the varying levels of obscurity that we need to create the accurate predictions that you see in the launch today of all these AI applications. Those took maybe years to actually develop the training and then the back pieces to actually move the model to create as close to a reality as we need today, so that we can actually perceive and use the computer and the computational resources that we have to make these predictions and these outcomes that we are looking for. And that leads to the major challenges. There's two large elements that come into play, and the first of which is associated with the actual writing of this code. I'm sure many of you here in the audience have dealt with partial differential equations once or twice, and maybe the last time was when you were at university. But writing down the derivations for each of these layers gets complex pretty quickly. And with that, actually parsing through and working through the derivations to actually build these models requires very high bandwidths of computing resources that you need available to actually simultaneously work through different data sets so that you can collate the approximations and actually build worthwhile models. And without further ado, I'm going to introduce Tim Woodard, who's going to look at the what NVIDIA has actually brought to the table and what advancements in software we actually have at our disposal today as engineers and as software scientists and data scientists to actually implement these radical updates within our industry.
Awesome. Well, thank you, Justin, for that awesome introduction to neural networks, and really what a great tee up for why even talk about GPUs in this context. If you go back in history a little bit to around the mid-2000s, 2012 thereabouts, this was the first time where GPUs began to be utilized for training neural networks. And Alex Krizhevsky out of the University of Toronto figured out that he could use a GPU to train a neural network much more rapidly and make it practical. And the reason is all those calculations Justin talked about are inherently parallelizable. And what is a GPU but a massive parallel computer? You know, there are tens of thousands of cores on a modern GPU. And for this reason, their great programmability and the ability to parallelize large workloads, they've taken off in the AI space. And since that time, since the ImageNet challenge that was handily won with a neural network back in 2012, we've seen this Cambrian explosion of AI models, many different kinds of neural networks applied to solving different kinds of problems, like convolutional neural networks and recurrent networks, you name it. Most recently, you've probably seen in the news the large language models like ChatGPT and others. And this is a great example of the growth of AI models in recent past. If you look back at ResNet, when that was first created, Justin talked about those hidden layers and all those parameters that have to be computed, the weighting values. There were tens of millions of parameters in a model back with ResNet. ChatGPT has billions of parameters, 175 billion parameters to train that are in that neural network. And larger models are approaching trillion parameters, and so you need a lot of parallel compute to get through those models. And so NVIDIA's worked over the years to develop a whole stack solution to training these models. And so this is maybe helpful to look at how does all this fit together in terms of what NVIDIA does. Obviously, we design and develop GPU technology and even CPUs and DPUs, data processing units. We'll talk about that in a moment. And then work with partners like Mercury to build systems that use these components to solve and address very specific workloads. But in fact, the vast majority of our engineers are focused on the software libraries and tools to leverage and harness that parallelization inherent in the CPUs and the GPUs that we create. And so there are libraries specifically for DNNs and fast Fourier transforms and linear algebra, and all of those can be applied to addressing these kinds of challenges. So it's for this reason, the great programmability of the GPU and its ability to parallelize very, very large workloads that GPUs have become very popular in the AI space, and why you see NVIDIA associated so often in the discussion with respect to AI. So here you see, we have over 1 billion GPUs out there that can all be programmed with CUDA and used to do AI training and inferencing. So this creates a vast market, and you're seeing just many, many industries pick up AI across the board. I think, again, to go back to ChatGPT is a great example. I think it was trained on tens of thousands of GPUs. So this is just a great opportunity to apply these tools to solve very real-world specific problems. And you can see some of the industries that are listed here, and certainly public sector is at the top of the list of a place where AI can have a great impact. So kind of moving on into some of the things that we work on at NVIDIA, beyond those low-level libraries that I talked about, we also work on building and optimizing the AI frameworks that are used, like TensorFlow and PaddlePaddle and PyTorch. These are the tools that data scientists use. They are all GPU accelerated, and we work to gather all of those dependencies and compile these libraries and frameworks, and then additional tools like Fleet Command for managing a whole cluster, and TensorRT for optimizing a network for inference, and Tau for training, adapting, and optimizing, and Triton Inference Server. These are all applications that NVIDIA provides. And then we provide these through the NVIDIA GPU Cloud, or NGC, which I'll come back to in a moment. So we have released recently a number of GPU architectures that are relevant to this discussion. Hopper is our latest GPU architecture, and it has a new capability for accelerating transformer operations. So these are key when you look at large language models, for example, where these, as the parameters grow, anything that we can do to optimize the training and inferencing on these networks is key. And one of the ways that we can optimize these workflows is by reducing precision where possible. So there's lots of floating point operations, and we've added support for 8-bit floating point, and that allows the training and inference to go significantly quicker for these massive language models. And then Bluefield DPUs. These are really phenomenal processors for offloading networking operations to SoC, so that we can alleviate the CPU and the GPU to do more important work. And so these are really powerful tools when we're looking at especially edge processing, where you have lots of inputs and outputs coming into the network. And then our Ada GPUs, our Ada Lovelace GPUs, these are especially great at graphics. And so there are different kinds of cores on the GPU. We have CUDA cores, we have Tensor cores, and we have RT cores. And Ada GPUs have RT cores, which accelerate ray tracing, which is an important capability when it comes to AI. And I'll come back to that in a moment as well. So I mentioned the software layers, and this is really, really important, because all of this great hardware and the capability of a GPU is really of no value if you don't have software that can leverage that capability. And so we work year over year to bring these massive improvements generationally with each GPU, and then optimize all the software layers to take full advantage of each GPU layer, of each GPU architecture. And you can see here, just over the last less than 10 years, we've seen massive speed ups, far outpacing what you would have expected with Moore's law, up to 26x. So really quite impressive. But it's not just within moving from one GPU architecture to the next. I want to draw your attention here to the darker green bars, where even with the same GPU architecture, we continue to optimize the software layers, and you'll see continued value in training performance and inferencing performance. So here, this is showing, if you went from A100 to H100, you're going to see a almost 7x performance increase. But even sticking with just A100 over the last couple of years, we've been able to squeeze out another 2.5 times performance. So quite impressive. And so for us, this is involving both ends of the spectrum with AI. It's not only the training, but also the inferencing. And this is, again, showing an example of what can be accomplished with training large AI models for natural language processing, and the ability to greatly speed up the training and inference, up to 134 times faster than if you were using CPU only. And I'll draw your attention to the bottom of the chart there, where it lists a number of popular AI frameworks. I want to reiterate that all of the AI frameworks that you may use are GPU accelerated and available to you on our NVIDIA GPU cloud. So NGC is a repository, a catalog of containerized applications and software libraries that are available to you that are ready to go. They're already optimized for taking full advantage of a GPU. And it's a great way to avoid the pain of having to go, acquire all the dependencies and compile libraries and sort through, everything that's needed to get up and running with AI. You can just download a container and be ready to run. So highly recommend that you look at the NVIDIA GPU cloud, the NGC catalog, to see what's available there. A great example of that is the Triton inference server, which can take train models and optimize them for deployment, and that can target specific hardware architectures and make decisions about, depending on the number of cores and the memory available at the edge, you can get the most out of the system that you're running on. And that's one of the containers that's available on NGC. And I would be remiss if I didn't mention Omniverse. So Omniverse is NVIDIA's platform for operational and industrial metaverse applications. And I think this is the tie into AI is really key here. We're seeing a great demand for training data for things like perception models. And we can create synthetic training data using a tool like Omniverse, which is able to create very realistic images and label them properly. So if you're working in the fields of computer vision or perception models, anything to do with virtual environments, in fact, then Omniverse is a great tool for building these metaverse or digital twin applications. To just briefly go over, again, some of the hardware architectures that are available, and Justin's going to go into a little more detail on how these things come together in a system in a moment. We have Hopper, so our H100, which is our fastest, most powerful GPU for AI and HPC. And it has the transformer acceleration capability that I mentioned before, for especially these really large AI models. Being able to tune the performance and the precision of those models is really key to get the most out of the training. If you're doing anything related to graphics, the Ada Lovelace architecture is ideal. It includes RT cores, which accelerate ray tracing. And that's really important for things like Omniverse that I just mentioned a moment ago. And then finally, the Bluefield architecture. So NVIDIA Bluefield DPUs allow you to, again, offload work from the CPU and the GPU for things like packet processing and security. So with that, I'm going to hand it back to Justin to wrap it up. Thank you.
Thank you very much, Tim, for talking about the software and hardware available from NVIDIA to actually make everything that we're working towards actually possible today. So with that, let's kind of take a quick look at what it is that we're building today. When it's not just the software that's going into it, we actually need the infrastructure in place to handle all the resources that we need to accomplish this. So if we look at the diagram here that I have listed, really what we're depicting here, if we were to flow from top to bottom, is this kind of architecture that in the first step, we need at the edge or at the point of inference, in each independent sensor feed that we're actually using to build our models. And these sensors themselves could be anything from radar data points to temperature sensors to even human information that we're receiving from personnel within the environments that we're working in that are feeding manually entered data points into an architecture. And then the next step that we work through is actually that collection element, where we have various nodes located near the edge that are taking in these data points and either serving in one of two functions, the first of which is purely the collection piece, or they could have advanced functions actually applied to them where they're pre and post processing those data points to remove noise or to modify the data sets to actually make them available to the whole architecture more readily so that they can go into the rest of the algorithm or the rest of the functions that we need. And then these collection points then are going to feed the data directly to either the on-site storage locations that we have available or directly to the cloud, or specifically directly to the actual heart of the architecture. And this is that the machine learning cluster that could be one system all the way up to maybe 1,000 systems that are working in parallel to work through these complex problems and to make adjustments to the trained models with the latest set of data that we've received and the previous sets that we've received from the field to actually make a living, breathing algorithm that's being trained in real time alongside the actual prediction elements that we need, making them more and more accurate as time moves forward. And then finally, all three of these elements, that on-site storage, that cloud storage, and the actual compute nodes, then need to be accessible where we need it the most. And that's once again back to the edge, where we need to make real-time decisions and actually act upon the predictions and inferences that we received from our architecture up to that point. And then that's the basis of what we're building today, is these complex, massive systems that are actually feeding information to where we need to act in a moment's notice to employ those decisions that are being built upon. And we do this by that sensor integration of making them readily available over our networks and the data that's being pulled readily available within the architecture. And then we just pull it all together and create these predictions. But to make this work, I know we always talk about SWAP, the size, weight, and power of a system. But if we were going to break it down to its essence of what we're truly saying with those statements within our industry, we're talking specifically about putting the right system in the right place at the right time. If it's a computational node, it needs to have the capacity to work through the data sets. If it's a data collection node, it needs to have the expansive storage availability that we need to actually build upon it, and so on. And we have to specify specifically in the architecture where these elements are going to be and where they're going to be fielded and how they're going to operate. And with that, there needs to be care and careful consideration applied to the actual latency of these systems. We need to look holistically, not just at the internal latency of working through the PCI lanes and the storage and RAM that we have available to us, but we need to make it infinitely accessible to the architecture as a whole. So looking both at the internal latency of the system to punch through the data and the external latency to make the data available is crucial for making the systems actually work. And we have to dive in as deep as we can to the actual compute density and making them as robust as possible to actually fulfill the needs that we're dealing with. And we need, once again, to have that data available everywhere within our network when it's needed, with real-time access to the storage nodes and the actual compute deep learning nodes. And we need to apply as much rudimentary pre and post processing to the data as we can as it's flowing through our network to reduce the lead time in making the data available to be trained. And that's where we kind of look at these applications of where we could field them. And the first part is the obvious, that sensor data analysis and working through what we're actually perceiving in all of our nodes in the field. This could be anything from radar to sonar data and identifying the objects within our space, and then being able to dive into a classification based on maybe this one isolated area of the sensor sets. And then by pulling them all together, we can actually build these complex predictions of whether there's movement involved or where objects are located or where they're moving to or where they originated, all the way down to whether or not there's an action that needs to be implemented against them. And it creates this robustness to our actual critical systems and being able to manage all of the elements that we have at our disposal when it comes to interacting within our environment. Whether that's handling the safety critical infrastructure of advanced networks such as electrical power grids, or looking specifically at other industries where we truly need that capability to understand from 1 second to another what is going on within our infrastructures and making these actions as they are needed to actually work through them. And with that, Mercury, our position is actually trying to enable all the elements of the edge and bring together the capabilities that are required to be successful in any mission that we're employed on. Specifically today, we're looking at the data to decision side of the Mercury processing platform. And that is where we're actually pulling in that mission compute, the sensor processing, the communication capabilities of being able to transmit this data. And then finally, that command and control, or that critical systems management that I just discussed, of being able to employ these elements where needed. And with that, I'd be remiss if I did not discuss a little bit the advancements that we've made at Mercury of making all the hard work and the software acceleration and hardware capabilities that are available from NVIDIA on our latest platform, the Res X08 family of rugged servers. The first big advancement that we've pulled into this generation is we've integrated the latest silicon from Intel, the previously codenamed Sapphire Rapids family, which allows up to 56 cores per slot that actually helps with that compute node and the computations that are required in the data offloading to actually pass between the GPU for the deep learning and the actual inference, and then pushing out of the node for that holistic low latency architecture. Which brings me to the point of, with this generation came PCIe Gen 5, which doubled that internal bandwidth and allowed for further advancements within our external network capabilities to make the data accessible not only internally but externally to the architectures as a whole. And with this generation also came the advancement to DDR5, which increased our total frequency that we have to work with the data inside of our random access memory to offload the short-term data and apply it to where it's needed in our architecture, whether it's a holding point before the data is passed to the GPU, or it's a holding point before the post or pre-processing that I was discussing earlier. And these servers come in various form factors, as I'm sure everybody here has worked with servers at some point in time in their career, that they come in 1U and 2U and 3U rack heights and between 18 to 23 inches in depth. The one that the Mercury product that I really want to talk about, though, really capitalizes on that DPU architecture that Tim was talking about earlier. And this one gets me really excited about the future of our industry. And this is the disaggregation of our compute resources to actually focus in on that swap and that right system at the right place at the right time to complete our missions. So what you get with that DPU is, instead of dropping in a server that's specifically in place to host these GPUs in parallel to run through these calculations, we can remove all of that overhead and specifically focus on the GPU's resources that are required and make it accessible over the network, so that our control unit can actually talk to the units within the array that I showed in my diagram and actually pass the data points directly to the GPUs as they're needed, and build these inferences and train these models in real time without, as I said, that overhead of the electrical and thermal requirements of running a full built-up x86-based architecture. And this is, I believe, the future of our industry is driving towards these disaggregated nodes that are function built and specific to their elements within these large architectures. And with that, I'm out of time, and I'd be happy to answer your questions, as I'm sure Tim is. And I'd like to thank everybody for coming.
Great. Thank you, Justin. Thank you, Tim. We have some questions for our audience that we can go ahead and get to. Tim, I'll start with you. So the question we have is, can I use the same GPUs for AI training and graphics workloads?
That's a great question. I think this is one of the really awesome benefits of a GPU. They're quite capable at multiple kinds of workloads, especially with respect to the L40 and the A40 GPUs previous architecture. So these in A6000s, these allow for all kinds of general purpose computation, from AI to computer graphics to HPC. It's very, very programmable. So whether you're using CUDA or a graphics API, you have lots of options available to you when using a GPU. So in short, yes, you absolutely can. If you're going to be doing non-interactive graphics, you can even use the A100 and the H100 for things like synthetic data generation.
Great. Thank you for that. Justin, we have a question. Are classification algorithms really applicable to defense?
So yes, that's the short answer. The longer answer, though, is we got to look at it in terms of granularity and obscurity. Of course, you have classification algorithms that are simplified to the point of classifying an image and ascertaining whether or not there's a cat or a dog in the picture. But really, what this gives you is that capability to do those deeper dives into what it is that we're trying to understand within the world around us. Just because we're applying a classification around it doesn't mean that that data isn't useful when it comes to the battle space. For instance, the classification instead of cat or dog could be threat level with that probabilistic algorithm that I was discussing earlier when it came to the neural networks design. And that threat level could then be translated into action that is required on the field or tasking of resources that we have available to us to accurately intercept or work with threat level that we perceive in the world around us. Or it could go as deep as to logistics prediction, whether or not that there is specific supply constraints that could be seen with the environment as it's evolving within the space that we're operating.
Great, thank you. Back to you, Tim. What are CUDA cores, RT cores, and tensor cores used for?
Sure. Yeah. So CUDA is the programming language that we use to pass off parallel work to a GPU, and the CUDA cores are general purpose cores on the GPU. There are thousands of them. They're really great at mixed workloads. So all kinds of linear algebra and many different kinds of processing can be done on the CUDA core. In addition to the CUDA core, though, we also have two other kinds of cores that accelerate very specific kinds of work. And the first I'll mention is tensor cores. And tensors, they're just vectors, right? So with tensor cores, we can accelerate these very important operations in AI training and inferencing, namely these mixed precision matrix multiply add operations that are really fundamental to the back propagation and the forward propagation that was mentioned earlier. Tensor cores accelerate that. And those are accessed through the CUDA programming language. But of course, if you're using one of the AI frameworks I mentioned before, that's already been done for you. That work's been done. In addition to tensor cores, we have RT cores. And RT stands for ray tracing. And ray tracing is a very important operation when it comes to computer graphics and generating realistic images. And so RT cores accelerate the ray triangle intersection test. That's key in those kinds of workloads. Interestingly, RT cores can be used for things beyond just visible spectrum computer graphics. There are applications in imagery orthorectification and sensor processing of things like LiDAR and radar. So having the ability to use all of these cores is really pretty incredible, especially when you have a workload that benefits from parallelization, AI, and computer graphics.
Great, thank you for that. Justin, with the increase in TDP, how has Mercury optimized swap size, weight, and power?
So yeah, you're whoever asked the question is correct that the TDP of the latest generations is exponentially growing, and that's the heat at which it's and the power that's being consumed within our architectures, and the heat that we need to disperse. The best way that I can point to this is the example of the flagship model of the Res X08 family, which is the first one that we're working to release, which is the 2U18R family. This unit is a short depth 2U system that's built to support those large Xeon Platinum processors that we have available with the latest generation and dual socket configuration. But at the same time, with our thermal management systems that we have in place and our proprietary or in some cases patented technologies that we have for thermal management and the direction of airflow within the architectures, we're able to even put in two H100s with NVLink to work with the applications that we're actually building towards. Of course, depending on the architecture and the constraints that we have available within our environment that we're operating, we would have to work with some of the elements in place. But with this generation, we have taken a stance of developing these architectures and growing so that we can rise to the challenges that's associated with operating with higher temperature components. And this is something that we strive to improve upon every day, and to develop specific applications that are based around optimizing the real estate that we take up and providing the compute that's capable with the technology that we have today.
Great, thank you for that. Tim, where can I see the list of available GPU optimized containers?
Yeah, so the best place to look is ngc.nvidia.com, and there you'll see the whole catalog of containerized software for AI, for HPC, for all kinds of workloads that are GPU accelerated.
Okay. Well, I want to thank you all. We have reached this brings us right to our time limit for today. Sorry we could not get to all of your questions today. Someone may get back to you after the event with more information. I would like to thank Justin and Tim for speaking today, and Mercury Systems for sponsoring this webcast. This and all Open Systems Media webcasts are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This event will be archived online today at the same URL you used to join today's live session, as well as at the URL shown on your screen. It will be available for at least 1 year. I look forward to seeing you on future Open Systems Media webcasts. Goodbye.